Welcome back, design junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. Today, we're setting up a virtual workbench, and we're pulling up the heavy reference materials.
Oh yeah, we are definitely getting into the weeds today.
Yeah, you are stepping into an advanced session on the hidden, really invisible forces that make or break our structures. We are talking about stress concentration factors in notches and grooves.
Right.
And to really set the stakes here, I want to rewind, back to the 1950s, to the dawn of the jet age, the de Havilland Comet.
Ah, the comet.
Right. It was the world's first commercial jetliner, an absolute marvel of engineering at the time.
It really was.
But then they just started falling out of the sky. Mid-air disintegrations.
Yeah.
Total catastrophic failures.
Yeah, and it remains one of the most sobering lessons in the entire history of structural design. I mean, when investigators finally recovered the wreckage from the ocean floor and reassembled it, they found that the fuselage had literally ripped apart.
Just unzipped.
Exactly. And the origin point for that massive structural failure, it wasn't the engines, and there wasn't the wings either. It was the corners of the passenger windows.
Because the windows were square.
They were essentially square, yes. I mean, they had slightly rounded corners, but structurally speaking, they behaved like a square punch-out.
Right.
The engineers had designed the cabin to be pressurized for high-altitude flight, which meant the fuselage was constantly expanding and contracting.
Yeah.
Inflating and deflating like a balloon over and over.
Like every single flight cycle.
Every single time. And the basic math for the aluminum skin said, well, it was more than thick enough to handle that pressure.
Okay, so the baseline math checked out.
It did, but that basic math assumed a continuous, uniform cylinder. It completely failed to account for what happens when you cut a large, basically square hole into that cylinder.
And that oversight right there is the entire foundation of what we are unpacking in this deep dive.
Yeah, it really is.
We are looking at why a part almost never breaks, where the macro level math says it's uniformly stressed. It breaks at the discontinuities.
Always.
Right? Like a shoulder relief groove on a transmission shaft, or a snap ring groove, a bolt thread, the corner of a square window, or even just like a tiny accidental scratch on a massive steel tension rod.
A single scratch can grow the whole thing down.
Exactly. So our mission today is to understand not just what a stress concentration factor is, but the actual physical mechanics of why it has the power to cause a massive, seemingly indestructible piece of machinery to just snap.
And we're going to look at how engineers mathematically model that invisible threat, how different metals react to it, and ultimately how we design our way out of it.
But before we get into the heavy math, I want to throw out a hook that we are going to explore later in the session, because I was looking through the lab data and there is this completely counterintuitive geometric reality.
Oh, this is my favorite part.
Right. Adding more notches to a part actually cutting more holes or grooves into your solid steel can make it stronger than having just one notch.
Which is wild, right? You'd naturally assume that if a cut is a weak point, well, making more cuts is just adding more weak points.
Yeah, it feels like structural sabotage.
It does. But when we start looking at how stress physically flows through a solid medium, you find that you can actually use geometry to trick the forces into bypassing your weakest links.
I am absolutely holding you to that, because right now it sounds like magic.
Fair enough.
But let's build the foundation first. Let's define the math. If I take a standard mechanics of materials class, the very first formulas I learn for tension or bending, they assume a pristine, perfect shape, a constant cross-section. Force divided by area equals stress. It's incredibly simple.
It's simple, and it's also almost entirely useless for a finished mechanical part.
Right?
Because real-world parts have to interface with other parts. They need shoulders to rest against bearings. They need holes drilled through them for pins.
Keyways milled into them.
Exactly. Keyways to lock onto gears, or grooves for oil slingers. Every single one of those geometric features is a discontinuity. And when you interrupt the physical material, you fundamentally modify the stress distribution. You create a highly localized high-stress zone.
Okay, so let's quantify that localized spike. The engineering models use a specific multiplier for this, designated as KT for normal stress like tension or bending, and KTS for shear stress, which is twisting.
Correct.
So the spoken math definition for KT is sigma max divided by sigma nom,
Right.
meaning the absolute peak stress in that localized disturbed region divided by the nominal baseline stress.
Yeah, and that subscript T in KT, that is carrying a lot of weight.
How so?
It stands for theoretical. It tells us that this multiplier is derived from the pure theory of elasticity, or, from highly controlled laboratory experiments using photoelastic models or finite element computer simulations.
So it's perfectly ideal.
Right. It assumes your material is perfectly elastic, perfectly uniform, and has zero internal flaws. It's a mathematical ideal. But the real friction in the engineering room happens when you try to define that denominator, the nominal stress. Sigma nom.
Okay, let's unpack this, because there isn't just one way to define the baseline area, right?
No, there isn't.
If I have a flat rectangular steel bar being pulled from both ends, and I just drill a hole right through the middle, I now have less material. So when I calculate my baseline stress to figure out my multiplier, I have two choices, KTG and KTN.
Yeah, let's look at the gross area first, which gives us KTG.
Yeah.
If you calculate the baseline stress using the full original width of the bar, completely ignoring the fact that a hole even exists, you are using the gross area.
Okay.
You take your pulling force, divide it by that large, unbroken cross-section far away from the hole, and that's your denominator.
See, that makes the most logical sense to me. You want to compare the broken, stressed part to what it was originally supposed to be. You want to see how much damage the hole did compared to the pristine bar.
It makes historical sense, perhaps, but mathematically, it leads to a massive distortion as the geometry changes.
Why is that?
Well, let's take that hole and start making it bigger and bigger. As the hole diameter approaches the total width of the bar, meaning you are hollowing out almost the entire part, leaving just two paper-thin slivers of metal on the edges, what happens to KTG?
Well, if the hole takes up 99% of the bar, those tiny slivers of metal are taking an unbelievable amount of stress.
Right.
So the peak stress, sigma max, is astronomical. But the gross area, my denominator, hasn't changed. It's still calculating based on the full original solid width.
Exactly.
So my multiplier, KTG, it must just shoot straight up to infinity.
It does. It approaches mathematical infinity.
Right.
And that tells you absolutely nothing useful about the localized behavior at the edge of the hole.
Ah.
You're comparing an extreme local peak to an irrelevant, massive bulk area that doesn't even physically exist at that cross-section anymore. That is why engineers rely on KTN.
The net area.
Yes. For KTN, you calculate the nominal stress at the exact cross-section of the hole. You physically subtract the diameter of the hole from the width of the bar to find your remaining net material.
Got it.
And then you assume the force is distributed uniformly across whatever small amount of metal is actually left.
Okay, let me test this. We have our bar with a massive hole, leaving just two tiny slivers of metal. If I calculate the stress uniformly across just those tiny slivers, that's my net nominal stress.
Right.
And KTN is the peak stress at the very edge of the hole divided by that net nominal stress. But wait, the data shows that as the hole gets huge, KTN actually drops down toward 1.
It does.
It goes down.
How is that possible? The part is obviously incredibly weak and about to snap. Why does the stress concentration factor go to 1?
Because you're conflating overall part strength with localized stress concentration. They're not the same thing.
Yes. The part is incredibly weak because there is almost no material left. But KTN isn't measuring overall strength. It's measuring the gradient. It's measuring how much worse the stress is at the exact edge of the hole compared to the average stress in the remaining material right next to it.
Okay, I think I get it. It's like a traffic jam.
Let's hear it.
If I have a massive 5-lane highway and a crash closes down one lane, you have 4 remaining open lanes. All the cars from that closed lane have to swerve, brake, and violently squeeze into the other 4 lanes.
Yep, lots of chaos.
That bottleneck, that chaotic swerving, is your high stress concentration. The peak stress right next to the crash is way higher than the average stress of the highway.
Keep going with that. What happens when the hole gets huge?
If the hole gets huge, it's like shutting down 4 out of the 5 lanes. But actually, no, that doesn't fit because KTN uses the net area. If the net area is tiny, it means the whole highway is just a single-lane dirt road to begin with.
That is the exact visualization. Stress flows through a solid part, very much like fluid or like traffic. When you have a massive block of material, the 5-lane highway, and you put a small obstruction in it, the stress lines are forced to rapidly bend, compress, and bunch up to get around the obstacle.
And that violent bunching is your stress spike.
Right. Your multiplier is high.
But if the obstacle is so massive that the only remaining material is a tiny, thin ribbon on the edge, well, that ribbon is essentially just a 1-lane dirt road.
Exactly.
The stress lines don't have to abruptly swerve or bend around a bulk of material because there is no bulk material left. The stress just flows straight through the thin ribbon.
Precisely. The traffic is moving slowly because it's a dirt road, meaning the overall nominal stress is very high. But there's no localized bottleneck within that dirt road. The stress is uniformly high across the entire thin sliver.
Wow.
And because the peak stress is roughly equal to the average stress, your KTN multiplier drops to 1. There was no concentration, just uniform high tension.
That distinction completely changes how I look at a mechanical drawing. KTN is strictly telling us about the severity of the bottleneck, the traffic jam itself, and that severity is entirely dictated by the geometry of the obstacle, the shape of the notch.
The shape is everything. A deep, hyperbola-shaped notch in a massively wide plate forces the stress flow into a severe, violent detour. A shallow, U-shaped groove in a narrow bar forces a much gentler detour.
That makes sense.
And the boundary conditions matter just as much as the notch itself.
Because the outer edges of the physical part push back on the stress flow.
Yes. If you have an infinitely wide plate, the stress lines can take as wide a detour as they need to get around a hole. But in a real physical piece of metal with finite edges, the stress lines are trapped. They're squeezed between the hole and the outer boundary of the part. This creates a highly complex mathematical environment.
And before modern computers and finite element analysis software, calculating that squeeze for every single unique shape a designer came up with was practically impossible.
Oh, absolutely impossible.
Which is where Heinz Neuber enters the picture.
Yeah, Neuber's work in the mid-20th century is just legendary in this field. He recognized that calculating exact mathematical solutions for every finite part was impossible. The math was just too dense.
Right.
But he had exact, elegant equations for two extreme theoretical cases. He knew exactly how a shadow elliptical notch behaved in a semi-infinite wide member. And he knew exactly how a deep, hyperbola-shaped notch behaved in an infinitely wide member.
So he had the math for a tiny scratch on a massive block and the math for a deep canyon on an infinite plane.
Right.
But neither of those are a real-world finite machine part.
No, but Neuber theorized that a real-world notch and a finite part was essentially a geometric compromise between those two extremes. So he developed an ingenious interpolation equation.
Like a mathematical bridge.
Exactly. He mathematically blended the stress concentration factor of the shallow ellipse with the factor of the deep hyperbola. By combining these two theoretical anchor points, his formula allowed engineers to accurately estimate the real-world KTN for almost any arbitrary notch in a finite width member.
It's basically a mathematical sleight of hand. He couldn't solve the real problem directly, so he combined two imaginary problems to perfectly predict the real one.
That's a great way to put it.
And that reliance on ellipses brings up another incredible shortcut used in stress analysis, the equivalent elliptical notch.
Oh, this is a vital tool for dealing with complex manufacturing realities. Think about a keyhole notch. It's a circular hole, but it's connected to the outer edge of the material by a straight saw cut.
Right, like an old keyhole on a door.
Or think about a rough, jagged corrosion pit. Trying to mathematically define the exact stress gradient along every microscopic millimeter of a jagged, complex curve is a nightmare, even with modern computers.
So instead of modeling the jagged mess, you just draw a smooth oval around it.
It's a bit more precise than just an oval. You envelop that complex, ugly shape inside a mathematically perfect equivalent ellipse. Laboratory testing proved that as long as the imaginary ellipse has the exact same depth as your complex notch and the exact same radius of curvature at the very root of the notch, it will generate almost the exact same overall stress concentration factor.
Oh, wow.
Yeah. The stress flow doesn't care about the complex squiggles halfway down the cut. It only cares about how deep it has to dive and how sharply it has to turn at the very bottom.
The spoken math for this equivalent ellipse is surprisingly clean, too. It states that KTT equals 1 plus 2 times the square root of the quantity. Depth of the notch divided by the radius at the root.
Right.
So depth is t, radius is r. So 1 plus 2 times the square root of t over r.
It's a beautiful equation because it instantly exposes the physical relationship. The depth t is your numerator inside the square root. So the deeper the notch, the higher the stress multiplier.
And the radius r is your denominator.
Exactly. So the sharper the cut, meaning a smaller radius, the more that fraction explodes and the higher your stress multiplier goes.
Okay, let me run a standard shape through that equation just to see. What if I just have a perfectly smooth semicircular cutout on the edge of a plate? A half circle.
Okay, let's do it.
For a perfect half circle, the depth of the cut into the material is exactly equal to the radius of the circle. So t equals R.
Right.
So the ratio of T divided by R is exactly 1. I plug that into the spoken math. KT equals 1 plus 2 times the square root of 1.
Uh-huh.
The square root of 1 is 1. 2 times 1 is 2, plus 1 is 3. So KT equals 3. A smooth, simple half-circle cutout instantly triples the localized stress.
It absolutely triples it. And that value, KT equals 3, is essentially the benchmark constant of stress analysis.
Wait, really? Just a constant benchmark?
Yeah. If you take a massive infinite solid plate and drill a perfectly round hole right through the center, the stress at the edge of that hole is exactly 3 times the nominal tension. It is the permanent baseline reminder to every engineer. The moment you introduce a perfectly smooth circular void into your material, you have automatically multiplied your localized stress by 3.
That is wild. But, we've spent this entire time talking about the geometry, the shapes, the traffic jams of stress lines. But KT is just a theoretical multiplier.
Very true.
It assumes the material is perfectly elastic forever, a theoretical mathematical spring. But a steel shaft and a glass cylinder don't fail the same way, even if they have the exact same shape.
Not at all.
We need to look at what physically happens to the atomic structure of the metal when you punch it with triple the stress.
And this is the critical transition from theoretical mathematics to material reality. When you move from the chalkboard to the physical workbench, you stop looking at KT and you start looking at KE, the effective stress concentration factor.
Yeah, okay, so KE.
Right. KT is what the pure geometry predicts. KE is what actually happens when you load the physical part until it breaks.
And whether KE matches KT depends entirely on whether your material is ductile or brittle.
Exactly.
Let's start with ductile materials like standard mild structural steel or pure aluminum. What happens at the atomic level when that KT of 3 hits the edge of a hole?
Well, mild steel is ductile because its atomic lattice structure allows for slip planes. When you apply a static pull to a steel bar with a hole in it, the stress at the very edge of the hole quickly triples.
Right.
As you pull harder, that localized peak stress sigma max rises very fast until it hits the yield strength of the steel.
The yield strength is the point where it stops springing back and permanently deforms.
Yes. The atoms literally slide past one another. The steel at that microscopic edge yields, it stretches plastically. But the crucial part is what happens next. Because it yields, it physically cannot hold any more stress. Its capacity to take on more load maxes out.
But you are still pulling on the bar.
Right. So where does the extra force go?
It has to go around the yielding zone. It bleeds out into the surrounding, less stressed material further away from the hole.
Exactly. The yielded material essentially acts like a microscopic shock absorber, passing the buck to the neighboring atomic layers. The stress profile flattens out. The high peak is chopped off and distributed.
Oh, that's fascinating.
Because of this localized yielding and load sharing, the physical danger of the notch is heavily mitigated under a static load. The effective stress concentration factor, KE, drops significantly down toward 1. The part survives because the ductile material literally reshapes its own internal geometry to alleviate the traffic jam.
The material auto-corrects the engineer's geometric flaw. That is incredible.
It really is a lifesaver for engineers.
But brittle materials like glass, ceramics, or very highly hardened tool steels, they don't have slip planes. They don't yield.
They do not. Brittle materials are locked in tight atomic bonds. They act totally elastically right up to the exact moment their bonds tear apart. They don't stretch. They don't share the load.
So they just take the hit.
They take the full, concentrated force of that KT multiplier right on the chin. When the peak stress hits the ultimate tensile strength of the brittle material, a microscopic crack forms, propagates at the speed of sound, and the part violently shatters.
Wow.
For a brittle material under static load, your effective KE is essentially equal to the theoretical KT. You take the full damage.
But the lab data brings up a bizarre outlier here. Gray cast iron.
Oh, yeah.
Engine blocks used to be made of this stuff constantly. It is notoriously brittle. You hit a cast iron skillet with a hammer, it shatters, it doesn't dent.
Nope, just breaks into pieces.
Yet the data shows that for gray cast iron, the effective factor, KE, actually drops down toward 1, behaving almost like a ductile material under static load. How does a brittle material survive a massive notch?
It survives because of a beautiful irony of metallurgy. Gray cast iron is brittle at the macro level, but if you look at it under a microscope, it is a chaotic mess. The carbon in gray cast iron precipitates out during cooling and forms millions of tiny, sharp, jagged graphite flakes distributed randomly throughout the iron matrix.
So the material is naturally saturated with microscopic cracks.
It is entirely pre-ruined. Every single one of those microscopic graphite flakes acts as a severe internal stress raiser. The material is already dealing with millions of tiny, high KT multipliers internally.
Oh, I see where this is
So
going.
if you come along and machine a macroscopic U-shaped groove into the side of a gray cast iron bar, it hardly makes a difference. The localized stress spike from your groove is competing with the millions of stress spikes already inherent in the material.
That is
The
hilarious.
macroscopic notch doesn't introduce a massive new weakness relative to the baseline. Therefore, KE approaches one.
It's immune to bad geometry because it's already universally terrible geometry.
That's exactly it.
But let's step away from one-time static loads. Everything we've discussed so far assumes you were just pulling apart once until it yields or breaks. But in mechanical engineering, shafts spin, wings flap, engines vibrate. We're dealing with cyclic loading, fatigue,
Right.
and fatigue changes the rules entirely, even for ductile materials.
Fatigue is the great equalizer. A ductile steel part might yield and save itself if you pull it really hard one time. But if you pull it, release it, compress it, and pull it again thousands or millions of times, that localized yielding at the root of the notch becomes a problem.
Because it's moving back and forth.
Yes, the atomic slip planes slide back and forth, rubbing against each other. Eventually, that friction causes atomic bonds to break. A microscopic crack initiates at the root. And once a crack forms, the sharpness of the crack root creates an astronomical KT multiplier, causing the crack to fly straight through the part over time.
To deal with this, engineers use a concept called notch sensitivity, denoted by the letter Q. And there is a specific formula to calculate the actual fatigue damage you can expect, called the estimated fatigue notch factor, KTF.
The fatigue notch factor is what you actually use to design a spinning shaft.
So the spoken math for this is KTF equals Q multiplied by the quantity KT minus 1, and then you add 1 to that whole result.
Let's look at what the notch sensitivity Q is actually doing as a dial in that equation. The value of Q is a material property that ranges from 0 to 1. If your material is completely insensitive to notches under fatigue, meaning Q equals 0, then that middle mathematical term vanishes. KTF simply equals 1. The notch does 0 extra fatigue damage.
And on the other extreme, if the material is incredibly sensitive to the notch, if Q equals 1, then the equation simplifies so that KTF exactly equals your full theoretical KT.
Yeah.
You take 100% of the theoretical geometric damage every single time the shaft spins.
Exactly. The notch sensitivity Q is determined through exhaustive, expensive laboratory fatigue testing for every specific alloy and heat treatment. It depends heavily on the grain structure, the ultimate strength, and even the physical size of the part.
So let's put this into a real-world scenario. I'm sitting at my desk. I'm designing a high-speed turbine rotor for a new generator, or maybe a heavily loaded axle shaft with a deep oil slinger groove. I've looked at the Nuber charts. I've calculated my theoretical geometric multiplier, K-Shi, and it's high, say, 2.8. But I'm using a newly developed proprietary steel alloy, and I do not have millions of dollars to run thousands of fatigue tests to find the exact notch sensitivity Q. What do? I guess?
You never guess with fatigue.
Right.
The structural integrity guidelines dictate a very clear golden rule for missing data. If you lack the specific empirical fatigue data for Q, you must assume Q equals 1. You assume the material is fully, catastrophically not sensitive, and you apply the full theoretical KT to your baseline fatigue calculations.
You assume the absolute worst-case scenario.
It is the only way to ensure you remain safely within the conservative design envelope. If you just assume the material will yield and save you, or if you guess the Q is 0.5 because it's a ductile steel, you are inviting a catastrophic failure. The geometry will find the weakness.
We've established that notches cause these massive stress spikes, and those spikes inevitably lead to fatigue cracks. So the logical, straightforward, common-sense solution is to eliminate the notches, polish them out, make the shaft perfectly smooth. Fewer cuts equals less stress.
That is the common sense assumption. And this is where we pivot to that hook we promised at the beginning of the session.
Yes.
The assumption that fewer notches equals less localized stress is fundamentally, mathematically wrong in certain specific configurations.
The multiple notch anomaly. This is easily the most fascinating piece of structural mechanics we've uncovered. How does adding more physical cuts into a solid piece of steel allow it to handle stress better than a part with only one cut?
We have to return to our flow analogy, but let's upgrade it from a highway to a fast-flowing river.
Okay.
Imagine a very deep, very fast river. If you drop a single, massive, sharp boulder Right in the middle of that smooth river, what happens? The water violently crashes into the front face, it accelerates wildly around the sides, and it creates violent, chaotic, churning eddies in the wake behind the rock.
So that severe localized disruption is your massive stress spike, your high KT.
Right. The single obstacle forces all the water to violently react at one specific point.
Okay, I'm with you.
But now, imagine instead of one rock, you lay down a long series of rocks spaced closely together, creating a corrugated washboard surface along the riverbed. The water hits the very first rock, and yes, there is an initial disruption. But then the flow dynamics change.
How so?
The water flow adapts. It glides over the tops of the subsequent rocks. The multiple notches guide the stress lines smoothly along the outer boundary, rather than forcing them to dive violently deep into a single chasm and violently climb back out.
Wait, so the stress lines essentially skip over the valleys between the tightly spaced cuts?
Exactly. Because the cuts or grooves are physically close together, the stress flow lines don't have the required physical distance to plunge all the way down to the sharp root of the next groove before they are forced back up by the next peak. The flow is bridged.
That is amazing.
As a result, the maximum stress concentration drops significantly for all the intermediate grooves in the middle of the sequence. Now, the grooves at the very beginning and the very end of the row still experience higher stress because they take the initial brunt of the flow diversion, but even they experience less total disruption than one single, isolated groove would on a smooth plane.
The reference materials actually cite a classic study from 1926, the Moore study that proved this wasn't just hypothetical math.
Yeah, the Moore study is a classic.
They ran physical fatigue tests, comparing a standard threaded bolt against a smooth bar that had a single V-groove machined into it, identical in depth and sharpness to the bolt thread.
And the physical test results were definitive. The fully threaded parts demonstrated considerably higher fatigue strength than the parts with only a single groove. Think about what a thread actually is. It's not multiple grooves. It is a single, continuous, tightly spaced spiral notch wrapping around the shaft.
Oh, right.
The grooves of the thread are so close together that they physically shield each other from the stress flow.
This clicked for me when I thought about competitive cycling. The peloton.
Oh, that's a good one.
Right. If you have one cyclist out front by themselves, they take the massive brunt of the aerodynamic wind resistance. That single cyclist is the single notch taking the full KT multiplier. But if you put a tightly packed peloton of 50 cyclists together, they share the aerodynamic drag. The air is forced to flow smoothly over the entire group as a single aerodynamic body. The threaded grooves are literally drafting off of each other. The leading thread deflects the stress wind, sheltering the subsequent threads.
That is a phenomenal way to visualize it. The aerodynamic shielding perfectly mirrors the elastic stress shielding. And structural designers use this multiple notch drafting effect deliberately to save failing parts. Let's say you have an axle shaft that absolutely requires a single groove to hold a retaining snap ring. And let's say that shaft keeps cracking at the snap ring groove during prototype testing. You can't remove the groove, the assembly requires it.
So what's the fix?
Sometimes the fix is to deliberately machine 3 or 4 dummy grooves into the shaft right next to the required groove.
Dummy grooves.
Yeah, these extra cuts serve no mechanical purpose for assembly. They exist entirely to create a stress peloton. They pre-divert the stress lines, creating a corrugated flow that shields the required snap ring groove, lowering its peak multiplier and stopping the fatigue cracks. You literally fix a crack by cutting more holes in the part.
That is structural judo, using the enemy's force against itself.
Perfectly said.
But the engineering tricks don't stop at just adding more grooves. You can also manipulate the physical shape of the very bottom of the cut to smooth the flow even further.
The profile of the notch root is highly sensitive. The lab data references extensive work done on solid propellant grains for rocket motors, where internal cracking is a catastrophic issue. They systematically found that modifying a standard semicircular notch bottom into a semi-elliptical bottom provides massive stress relief.
But earlier we established that a perfect semicircle was the standard benchmark, a KT of 3. Why isn't a perfect circle the best shape?
Well, it's the standard because it's cheap and easy to manufacture. A standard drill bit, or a basic ball-end mill, naturally leaves a circular profile. But from a stress flow perspective, a semicircle forces a fairly abrupt change in direction at the sides. If you take the extra manufacturing effort to machine a semi-elliptical bottom, specifically stretching the ellipse so that the width-to-depth ratio is roughly 2 to 3, you flatten the bottom of the curve slightly.
You're giving the stress lines a wider, gentler ramp to slide down and back up, instead of a sharp bowl.
Yes. And that slight geometric flattening can reduce the peak stress multiplier by up to 20% compared to the standard semicircular bottom.
A 20% reduction in peak stress just by slightly flattening the bottom curve of the cut. That isn't a marginal gain. In high cycle fatigue, a 20% drop in kick stress could be the difference between a helicopter rotor mast lasting 10,000 flight hours or suffering a catastrophic fracture in 200 hours.
Exactly. It all comes down to aggressively respecting the geometry.
Which leads us perfectly into the final and perhaps most critical segment of our deep dive. We've talked about pure tension, we've talked about pure bending, but real-world machinery does not operate in clean, isolated physics problems.
Real-world parts are chaotic. They're being pulled, twisted, bent, and vibrated all at the exact same time.
So it's time to set up our classroom walkthrough. We are going to directly answer one of the most popular questions engineering students and junior analysts struggle with when they look at combined loading scenarios.
The classic scenario: a drive shaft and a heavy machine. The shaft has a U-shaped circumferential groove machined into it. During operation, this shaft is subjected to a massive axial tension force pulling it apart. Simultaneously, the weight of a heavy flywheel is creating a bending moment, trying to snap it like a twig. And simultaneously to that, the motor is applying a massive twisting torque to drive the load. Tension, bending, and torsion all attacking the groove simultaneously. How do we find the true peak stress to see if the shaft survives?
Okay, let's break this down into clear sequential steps. Step 1. What is the fundamental requirement before we even look at a formula?
Step 1 is the boundary condition for the entire analysis. Ensure that all individual stresses remain below the elastic yield limit of the material. If the material starts to permanently stretch and go plastic, the geometry deforms, the stiffness matrix changes, and this straightforward math is completely invalidated. But as long as the steel remains perfectly elastic, behaving like a rigid mathematical spring, we can rely on the principle of superposition.
The principle of superposition, meaning we can evaluate each type of force completely independently in its own lane and then logically add the results together at the end.
Correct. You isolate the variables. So step 2 is to calculate the raw nominal baseline stresses for each of the 3 lanes, completely ignoring the fact that the U-shaped groove even exists for a moment. You just calculate the stress for the net solid core of the shaft.
Let's invent some dummy numbers to ground this. Let's say the net solid core of the shaft, the D diameter at the bottom of the groove, is exactly 1 inch, and let's say the axial pulling force, P, is 10,000 pounds. My nominal tension stress is just force divided by area. The area of a 1-inch circle is roughly 0.785 square inches. 10,000 divided by 0.785 gives me a nominal tension stress of about 12,700 psi. That's my first lane tension.
Exactly. Now move to the second lane, the bending moment, M. To find the nominal normal stress from bending, we use the standard flexure formula for a solid circular cross-section.
The spoken math for the flexure formula is 32 times the bending moment divided by pi times the diameter cubed. Let's say my bending moment is causing a nominal stress of 20,000 psi on the outer skin of the shaft.
And finally, the third lane. The twisting torque T torsion creates shear stress, not normal pulling stress. The formula for maximum nominal shear stress in a solid cylinder is 16 times the torque divided by pi times the diameter cubed.
So 16T over pi d cubed. Let's say that gives us a nominal shear stress of 15,000 psi. Okay, I'm a student at the workbench. I have my 3 isolated lanes. 12,700 psi tension, 20,000 psi bending, 15,000 psi shear twisting. Step 3.
Step 3 is where you introduce the geometry of the U-shaped groove back into the problem. You go to your reference charts, or you use Nuber's equivalent ellipse equations, and you find the specific theoretical multiplier for your specific groove shape. The critical detail here is that the groove disrupts different forces in different ways. You will have a specific KTN for the axial tension, you will have a slightly different KTN for the bending, and you will have a KTS for the torsional shear.
So I multiply my 12,700 psi tension by its specific multiplier to find the true localized peak tension. I multiply the bending by its multiplier to find the peak bending, and I multiply the shear by its multiplier to find the peak twisting stress.
Yes. Now you have the true amplified peak stress values for all 3 lanes.
Okay, step 4. I need a single number to compare against the material's yield strength to see if it breaks. Do I just take my peak tension, my peak bending, and my peak shear and add them all together mathematically?
No. If you just simply add them together, your shaft is going to snap, and you won't know why. You have to crash them together using the correct physics. Normal stress, which is the tension and the bending pulling the atoms apart, operates on a completely different physical plane than shear stress, which is twisting and sliding the atomic planes past each other. You can't adjust on them linearly. This brings us to the von Mises equivalence stress.
Explain the mechanism behind von Mises. Why does it work when simple addition fails?
It works because metals don't usually fail just because they are stretched. They fail when their internal atomic lattice distorts and changes shape. The von Mises criterion is based on distortion energy. It mathematically isolates the energy that is actively trying to twist to distort the atomic lattice, ignoring hydrostatic pressure that just compresses it uniformly.
And the reason we are allowed to crash these three specific stresses together into this one von Mises equation is geographic.
Precisely. The peak amplified tension, the peak amplified bending on the outer skin, and the peak amplified shear from twisting, they all physically occur at the exact same geographic microscopic location, the very bottom surface of the U-shaped groove. They are all attacking the same cluster of atoms simultaneously.
So how do we mathematically fuse them?
First, you linearly add your two normal stresses together, the amplified tension and the amplified bending. You can add them linearly because they are acting in the exact same direction, pulling along the axis of the shaft. Let's combine them and call that total normal stress sigma. Then you take your amplified torsional shear stress, and we'll call that tau.
Okay, I have my combined sigma pulling and my tau twisting.
The von Mises equivalence stress formula is essentially a geometric theorem for stress. It calculates the complex diagonal hypotenuse of these forces. The spoken math is sigma equivalent equals the square root of the quantity, sigma squared plus 3 times tau squared.
Wait, I remember a much longer, uglier version of the von Mises equation that uses principal stresses. Sigma 1, 2, and 3.
You're referring to the generalized 3D stress state formula. If you calculate the principal stresses for sigma 1 and sigma 2 on a 2D plane, the spoken math for von Mises is sigma equivalent equals the square root of the quantity, sigma 1 squared minus sigma 1 times sigma 2 plus sigma 2 squared. It looks different, but both formulas mathematically derive from the exact same distortion energy theory that will lead you to the exact same final equivalent stress value.
So the von Mises formula acts as a translator. It takes chaotic pulling and twisting forces, squares them, weights the shear heavily with that multiplier of 3, and spits out a single equivalent tension number.
Yes, it gives you one single number. And you simply take that single von Mises equivalent stress number and you look up the simple tensile yield strength of your steel alloy in a textbook. If your von Mises number is lower than the yield strength, your part survives the combined nightmare of forces. If it's higher, the geometry has failed you, and the part will fracture.
That is the ultimate magic of structural analysis. You take a chaotic, twisting, bending, vibrating, real-world machine, you break the forces down into simple isolated lanes, you amplify them by their specific geometric traffic jam multipliers, and you mathematically fuse them back together into one definitive pass-fail metric.
It is the closest thing engineers have to seeing the future. It takes the invisible forces trying to tear our machines apart and renders them visible, calculable, and controllable.
And that brings us to the end of our classroom session. Let's recap the intense journey we just took. We started with the de Havilland comet and defined how KT measures the geometry of an invisible stress traffic jam. We explored why understanding the flow difference between gross area KTG and net area KTN is critical so you don't end up chasing mathematical infinities.
We looked at how Heinz Neuber's brilliant historical approximation and the concept of the equivalent ellipse help us bypass the impossible math of complex real-world boundaries. We dug deeply into the atomic reality of materials, discovering why ductile slip planes can yield and save themselves, why brittle lattices violently shatter, and why gray cast iron is a bizarre immune exception because its microscopic graphite flakes mean it is already pre-ruined internally.
We proved that smoother is not always better. We used the river flow and the cycling peloton analogies to reveal how multiple closely spaced grooves and continuous threads actually draft off each other to lower the peak geometric stress. And finally, we walked through the practical workbench exam, superimposing tension, bending, and torsion loads at the very bottom of a groove to find the true distortion energy-based von Mises equivalent stress.
It's a comprehensive look at how structures fail. But before we close the workbench, there was one final, somewhat concerning reality from the physical sciences that I want to leave lingering in the air.
Let's hear it.
We spent time talking about how tiny surface scratches or minor grooves don't critically affect low-strength ductile mild steels because the atoms simply yield, stretch, and redistribute the load locally. But the structural testing data explicitly warns that as we push the absolute boundaries of modern metallurgy, as we design advanced, ultra-high-strength steel alloys and titanium matrices for cutting-edge aerospace and high-performance automotive applications, the rules invert.
How so?
Because the stronger you make the steel, the higher you push its ultimate tensile limit and lock its atomic structure to prevent yielding, the more inherently brittle and not sensitive it becomes. Its fatigue notch sensitivity Q skyrockets toward 1. In a low-strength steel pipe, a gouge from a wrench doesn't matter much. But in an ultra-high-strength, highly tensioned aerospace fastener, that exact same microscopic scratch becomes an astronomical KT multiplier that the material physically cannot yield away from.
So in our pursuit of absolute maximum material strength and weight reduction, perfection becomes a mandatory structural requirement.
Exactly. Our advanced materials becoming so incredibly strong, so highly tensioned and rigid, that they are now fundamentally fragile to a single microscopic manufacturing flaw. It is the great paradox of modern engineering. The stronger we build our materials to resist brute force, the more vulnerable they become to the invisible geometries of a microscopic scratch. It is a razor's edge that designers of the future are going to have to walk every single day.
The stronger we build them, the more delicate they become. What a thought to end on. Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.